Section 4.5 Multiplication Rule. Complements and conditional probability. Complements, at least one. In Section 4.4, we looked at the scenario tossing a fair coin 3 times and observing the outcomes. Our sample space contained 8 events, from tails, 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 all the way to heads, heads, heads. We had to be careful of how to calculate the probability depending upon the quantifier used, such as exactly versus at least. This time, we'll look at using the complement to help quickly find a probability when the quantifier at least 1 is used. Example 1. Consider the coin tossing example just described. Find the probability of getting at least 1 tail. Let's first attempt this using our conventional methods, what we know so far. At least 1 means 1 or more, so that means 1 tail, or 2 tails, or 3. So that includes the events tails, heads, tails. Now let's start with 1 tail each. So tails, heads, 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 tails, heads, and heads, heads, tails for just 1 tail, or for 2 tails, that would be tails, tails, heads, tails, heads, tails, and heads, tail, tail. But it also includes if we get 3 tails. So altogether we have 7 events. So that means the probability of at least 1 tail is 7/8. Well, now let's attempt that same problem using the complement. The complement of at least 1 is none. So the probability of at least 1, we're going to find the complement of that, which is the same thing as saying no tails or none. Well, the probability of no tails means I get all heads. So heads, heads, heads is what's in the example. That only happens one way, so that's 1 out of 8. But I'm still interested in finding the probability of at least 1 tail. Well, remember we subtract the complement from 1. So 1 minus the complement of at least 1 tail is 1 minus the probability of no tails, or 1 minus 1/8, which is 7/8, which we obtained above. So what you'll find many times is the calculations get a little bit long when you have to sum up at least 1, whereas it might be a little bit easier to find the complement none and then just subtract from 1 to get back to what you really want to find the probability of, at least 1 something. Let's try example 2. The probability that Mark's favorite restaurant does not have baked potatoes when he arrives at 6 p.m. is 0.25. During his next 3 6 p.m. visits to this restaurant, what is the probability that they will not have baked potatoes at least 1 time? First, let's identify what's going on here. I'm going to let B equal that a baked potato is available. So what we have is that a baked potato is not available, so we know the complement of B, which is 0.25. Okay, so if the probability that a potato is not available is 0.25, that means the probability that a baked potato is available is 0.75, using that complement rule there. We're interested in the probability that they will not have baked potatoes at least 1 time. The complement of that is that they will not have baked potatoes none of the time, which I know sounds kind of weird. It's a double negative. So what that really means is that they will have baked potatoes every time. So what we're trying to find is the probability that they have a baked potato on visit 1 and on visit 2 and on visit 3. And if we go back to our multiplication rule and thinking about these events being independent, then we can just multiply those together and say 0.75 times 0.75, or 0.75 raised to the third, which works out to 0.421875, or as a fraction, 27/64. So that time I took the complement early on and then kind of went from there. Conditional probability. When we learned about sampling without replacement, we introduced the conditional probability P of B given A, which indicates the probability of B given that event A has already occurred. Now we introduce an alternate formula for conditional probability. For two events A and B, the conditional probability of event B given event A is the following formula. The probability of B given A is equal to the probability of B intersect A, remember this intersect is the same thing as an and, divided by the probability of A. And what helps me to remember this formula is whatever order the two letters or events are over here when it says given, I put them in the exact same order over here with the intersection or the word and in the middle, and then I always divide by whatever was last. So in this case, A was second, so A is the one that I divide by. For that reason, in conditional probability, order is really, really important. The probability of B given A is not going to be the same most of the time as the probability of A given B. So it's up to us to pay attention to the language of the problem to understand which event occurred first and which one are we trying to find the probability of. Example 3. Suppose that 4% of all adults suffer from diabetes and that 29% of all adults are obese. Suppose also that 1% of all adults are both obese and suffer from diabetes. Part A. Find the probability that a randomly chosen adult who is obese also suffers from diabetes. Round your answer to 2 decimal places. Before we worry about that probability, let's write down the information that was given to us. Now they said that 4% of all adults suffer from diabetes. I'm going to let D represent diabetes. So the probability that a randomly chosen adult has diabetes is 0.04. Remember your decimal places with percentages. You're going to move that decimal 2 places. So it's not 0.4, that'd be 40%, but 0.04. Then we're also told that 29% of all adults are obese. So I'll use an O for obese, and that's 0.29. Then we have this last piece of information. 1% of all adults are both obese and suffer from diabetes. That word there is really important, that and. That lets us know we have an intersection. So we can write that as obese and has diabetes is 0.01. Now when you write down an intersection, it really doesn't matter which event goes first. I just wrote it down as it was given. So we had obese and diabetes, so I wrote it as O intersect D. Now that we have that written down, now let's see if we can work on part A. So we want the probability that a randomly chosen adult who is obese also suffers from diabetes. So this is where we need to be careful. What is the given? What do we know first? Well, they're telling us that the adult is obese. We know that much. So when I go to set up my probability notation, it's given O. That's the part I know first, that they're obese. What I'm interested in is the probability that that adult also suffers from diabetes. So the order matters. This says the probability that an adult has diabetes given that I already know that they're obese. So now when I go to use my conditional probability formula, I'll write this as the probability of D intersect A, or and A, or not A rather, I'm looking at the formula. We have an O for obese, divided by which one, D or O? What's going to be the second one? What came second? What came second over here, and what came second over here? So divided by probability of O. And we know all this information. The intersection between diabetes and obese, which is exactly the same as obese and diabetes, is 0.01. And the probability of being obese is 0.29. And I can plug that into my calculator. And I get 0.0345 if you round to the fourth decimal place. Okay, let's take a look at part B. Find the probability that a randomly chosen adult is obese given that he or she suffers from diabetes. Notice how the language is different this time. We know that they have diabetes because it said given that they have diabetes. This time we want to know what's the probability that they are obese. So my notation will change. This time it's going to be the probability that they're obese given that I know they have diabetes. So when I set up using my conditional probability formula, that's the probability of obese intersect with diabetes divided by which one? Whatever came second. So this time I'm going to divide by the probability of being or having diabetes. So this will be 0.01 divided by 0.04, and that should be 0.25. Okay, so really important that you pay attention to order and that you also pay attention to the language of the problem. Which one are they telling me that we already know, and which one is the one we're trying to find out? Example 4. Suppose that a certain college class contains 60 students. Of these, 33 are freshmen, 34 are biology majors, and 8 are neither. A student is selected at random from the class. A. What is the probability that the student is both a freshman and a biology major? B. Given that the student selected is a biology major, what is the probability that he is also a freshman? Okay, this problem actually has quite a bit going on, so we're going to introduce a Venn diagram to get a visual representation of this set. The way you draw a Venn diagram is you start off with the box, and the box represents the total sample space. So in this case, all 60 students. Next, you draw circles inside to represent each subset or event. In this case, our subsets are freshmen and biology majors. And we don't know how many freshmen are biology majors, meaning the intersection between the two. So we're going to overlap the circles to show that there is that possibility. So one circle is going to represent freshman students. And another circle will represent biology majors. So remember, the whole box represents all 60 students. If you, within the two circles, you're either a freshman or a biology major or both, and if you're outside of that circle, then you're not. So let's see what we have. We know that there are 60 students, and 33 are freshmen and 34 are biology majors. Part of the missing puzzle piece here, though, is we don't know how many students are both a freshman and a biology major. So that prevents us from filling in a lot of the information here. But we do know this. We know that 8 students are neither freshman or biology. So that goes outside here. It's within the box because it's within the sample space, but it's outside of the circles because those students are neither freshmen nor biology majors. What that leaves us with is that this portion here represents 52 students. Now again, I don't know the breakup. I don't know how many are just freshmen but not biology majors, and how many are just biology majors but not freshmen, or how many are both freshmen and biology majors. But collectively, these two circles together are 52 students, and that represents the union. So knowing that we have that breakdown now, let's see if we can write down parts of the Venn diagram that we do know. So we know the union, and I'm going to use F and B to represent freshman and biology major. So we know that freshman union with biology is 52 students. They also told us in the problem that, or I should say 52 out of 60, freshmen were 33, so the probability of being a freshman is 33 out of 60. The probability of being a biology major, we were told, was 34, so 34 out of 60. And here's one piece of information that might not be quite as obvious. It's that 8. Remember, those are the students that are neither freshmen nor biology majors. So that actually is the complement of F union B, and that is 8. Okay, so we have quite a lot of information there, or 8 over 60 rather. And I'm not going to bother to reduce my fractions yet because I'll probably need to add or multiply or something, and it's easier if they all have the same denominator. Okay, now that we have that information, let's see if we can answer parts A and B above. So part A says, what is the probability that a student is both a freshman and a biology major? So that freshman and biology major, that word should kind of ringing a bell in your head. That "and," if you remember, refers to an intersection. So we're trying to find, for part A, the probability that a student is a freshman and a biology major. Intersection and remember, they mean the same thing. Well, looking at that notation, F and B, or F intersect B, and the notation or the information that we have, F union B, probability of F and probability of B, those are all related with a certain formula that we learned earlier. It was the addition formula. So we know this much, that the probability of F union B is equal to the probability of F plus the probability of B minus the probability of F and B. So that's just our addition formula with F and B inserted instead of A and B. Well, we know a lot of these pieces. We know the union, 52 over 60. We know the F, 33 over 60, and B, 34 over 60. So the only part we don't know is F intersect B, which is what we're trying to find. Well, we can do a little bit of algebra and figure it all out. So 52 over 60, if I combine these two, that would be 67 over 60. And I'm going to call this part I don't know, I'm just going to call that X. So if I subtract from both sides, I end up with negative 15 over 60 equal to negative X because of this negative sign right there. Well, since both of them are negative, we can just say X is equal to 15 over 60, or 1/4. So the probability of F intersect B is 1/4. So we have to go back a ways and into some other formulas that we knew in order to figure that out. Now let's take a look at part B. B says, or is asking us, given that the student selected is a biology major, and that word given should be a big giveaway, what is the probability that he is also a freshman? So remember, this is important how we set up our notation. Given that the student is a biology major, that's the part we know. So when I set up my conditional notation, the B has to go second, given that he's a biology major. What is the probability that he's a freshman? That goes first. Now we can use our conditional probability formula. So that's the probability of freshmen intersect biology, which we thankfully found in the previous part, divided by which one? Always the second one, so divided by the probability of B. Well, we found the probability of the intersection, that's 1/4. Over, and I'm actually going to put that back in before I reduced it, so that it will be easy here to simplify. So 15/60ths, and the probability of B we said was 34/60. And a quick way to reduce is just to cancel the denominator since they're both exactly the same. That's 15/34, or 0.4412 if you take it out to 4 places after the decimal. Okay, so this problem, a very similar problem, appears in your homework. Probably the most important thing is making sure you label everything correctly, set up the equations correctly, and make sure you're especially paying attention to the order, both of the language and how you set up your conditional probability formula.